Welcome back to the course on Navi signal processing for music applications. This week we're talking about the harmonic model, and in these demonstration classes we're trying to understand this model by actually using it, by analyzing some sounds and synthesizing them. In this lecture I want to go a little bit beyond what we did and analyze a fragment of a sound and see if we can take it to the limit and see what is its potential and its limitations. So in particular, we will be analyzing a few notes of a cello that I played. And the cello is, of course, it's a great instrument. It's a very traditional instrument that you can do a lot of things with it. So a good way to get a grasp of the types of sounds that the cello does is look at free sound and just search for violoncello. Okay. And that will give you a few samples of different types of cello sounds. So in fact, for example, the first one is kind of an extended technique. In fact, let's listen to that. Okay, that's what is called a seagull effect, and it's kind of an interesting sound. Of course, you can also get some more traditional notes playing in what is called tenuto, or also with the cello you can play pizzicato notes, and this is a pizzicato note. But of course you can find many types of sounds and little fragments. The sound I will be using is a short cello phrase from a very traditional Catalan song, the Song of the Birds, and in fact it's the one that I use in the teaser of the course. In fact, let's listen to that one. Okay, so let's analyze this sound, and let's open the SMS Tools GUI, and we'll first start from the short time Fourier transform. This is time varying sound, so we need the short time Fourier transform to get a grasp of it. So let's open the sound, cello phrase right here. Okay, and we have to choose the parameters. And okay, let's, instead of a humming window, let's choose the Blackman window. The Blackman window, the main lobe is wider than the humming, but the side lobes are lower, and that may be good for this sound. So let's choose a Blackman window, and then window size we don't have much to decide from, but let's just, for example, let's use 1001 samples. Let's just leave the FFT size at 1024, and the FFT size, the hop size has to be at least 1/4 of the window size, so let's use 250. Okay, and now we compute that. This is a longer fragment, so it's going to take a little bit longer, and from it we will be able to visualize the magnitude spectrum and the phase spectrum. Okay, now what we are interested is in deciding what parameters are needed in order to be able to distinguish the harmonics of this phrase. So in fact, an important thing is to identify what is the lowest fundamental that is being played. The lowest fundamental will be the one that will determine the minimum distance between two harmonics. So let's zoom into the very bottom of this spectrogram. Okay, so this is the first and a little bit of the second harmonic, so it's a very clear harmonic sound. And we can see that it starts a little bit low, goes up, and then it goes down. So clearly the lowest frequencies are going to be the first and the last. But here we see that the resolution is not so good. In fact, we see these boxes, kind of this quantization in the horizontal axis. In the vertical axis is pretty good. We have 250 samples, so there is quite a lot of frames, but there is not that many in terms of frequency samples in order to be able to visualize and then further on analyze the peak of this harmonic. So let's increase, maybe the window size cannot be increased because then we would lose the time resolution, but let's increase the FFT size so we get a smoother spectrum, more samples. For example, let's say 4096, so quite a bit more of the FFT size. So this will give us quite a bit of zero padding, and therefore will give us many more samples in the frequency domain, even though the actual data points will be the same. So, well, again, this takes a little bit to compute. Okay, so this is the spectrum. Clearly, there is more fine resolution than before. Let's do the same thing. Let's zoom into the very bottom of the spectrum. Okay, and yeah, now we definitely have many more frequency samples, even though of course it looks similar, but we now would be able to see the center of the window much better. So if we look like in the last node, but with the center of these, now looking at the y-axis, it's around 348 hertz. Okay, so that would be the lowest node, and the highest node is around 456 hertz. Okay, so this is good information for deciding now the window size that we should use. So in fact, okay, let's do the sinusoidal model, and let's look at this information. So in order to decide what is the period length, so we have to take 44,100 and divide it by that frequency, which was around 300, let's say, and 40 hertz. Okay, to make it a little bit lower. Okay, so this is 129 samples, and then if we use, for example, the Blackman window, well, we will need 6 times that. So if we take 6 times these, okay, that would give us 778 samples. Okay, so let's put in the window size 778 samples. That should be enough to discriminate the harmonics. And the FFT size, I think it was good to have this big FFT size. So 4096 was a good choice, because that gave us a good resolution, at least visually. And now, of course, in the sinusoidal model, we can choose the threshold, the minimum duration of the sinusoids, and how many sinusoids we want to track, the maximum frequency deviation. Here we should, I think, have it a little bit bigger, because there is quite a bit of variation. Okay, and now let's, of course, choose the cello sound, the cello phrase, and we will compute it. Okay, so this is the sinusoidal analysis, and yeah, we see the harmonics following kind of the melody. We also see short sinusoids. In fact, if we zoom in into one region of that, for example, let's show this region here. Okay, we see well, definitely the harmonics, but also we see some lines in between them, and we see some trajectories stopping and continuing. So anyway, so this is sinusoidal model. If we listen to the result, well, it's pretty good. Maybe we are losing a little bit of the attacks of the notes, but it's pretty good. So let's go directly now to the harmonic model, and let's okay, use the cello phrase, and let's use the Blackman window. Let's use the same 700. Oh, we should have a knot size window, so let's use 779. In terms of the FFT size, again, okay, I think it was a good choice, 4096, a lot of zero padding. The magnitude threshold, -90, that's okay. The duration of the tracks, okay, so these will require to be 0.1 seconds. I think we can even make it bigger, so let's say 0.2 seconds. And the maximum number of harmonics, there is clearly no need for 100. In fact, a way to check how many harmonics are needed is if we divide 44,100 by the frequency, the lowest frequency. Okay, no, we have to divide half of the sampling rate, so 2250 divided by the lowest frequency, so 64. That would be the maximum number of harmonics that we would have if we really would have all the harmonics in the lowest note. So no need for 100. Let's say let's put 60 would be plenty. And here now is where we have to choose a range that includes all this melody. So we said that the lowest frequency was around 340. Let's make it safer, so let's make 300. And the highest was above 450 or something, so let's make it quite a bit higher just in case. Let's make it 500. Okay, and this is an error threshold that will be quite relevant now for identifying the fundamental frequency, but let's just leave it as it is now and see if we have to change it later. Okay, so now we will compute it. So again, this will take a little bit of time. Okay, so this is the harmonics it has obtained, and that looks pretty good. It found quite a bit of harmonics. Of course, in the transitions, that where the problems, or at least the little deviations occurs if we just zoom into just one transition, let's say. So this is where the harmonics, of course, get lost, and then they are picked up again. If we listen, well, let's plot it again to the original, and if we listen to the synthesize, okay, that's pretty good. Now, if in terms of this error threshold of the algorithm, if we make it more restrictive, so that means that unless it's below a certain error, it will not be accepted. We might see then that some of these areas it does not find the fundamental. So instead of 7, let's put, for example, 2. Okay, and let's see what it finds. Okay, so now we see the result, and we clearly see that in the transitions there are gaps. And this is because in the transitions the fundamental is not very clear. We are in a kind of attack, noisy attack, so it has lost a little bit of the transitions. And if we listen to that, in fact, we're going to listen to these gaps. Okay, so there are gaps in the transitions because that's where the areas that it didn't find the fundamental, and therefore it didn't find any harmonics. And that's basically all I wanted to say. So let's go back to the slides, and well, we have used the SMS tools GUI in order to analyze this cello fragment, and we have used the short time Fourier transform, the sinusoidal model, and now the harmonic model to see this phrase and to analyze the harmonics. And we can see that by tweaking the parameters we can get quite a bit of difference in the way that these harmonics are analyzed. So that's all, and this is all for the demo classes of this harmonic model week. So hopefully this has given you a view of how the harmonic model can actually be used in practice. And still is not ideal, and there is some parts of the sound, especially like in this sound that we just heard in the attacks, that we lose a little bit of the sound that is present there. So the next week we will extend the idea of the sinusoidal and harmonic model to include that aspect, to include what we call the residual or the stochastic component. Hopefully that will allow us to generalize our models and to be able to handle many more types of sound. So I will see you in next class. Thank you very much.